Okay, I think we're live. Let me just verify that everything is running smoothly on YouTube's end. Okay, it looks like we have a good stream. Okay, so welcome. Today is going to be an interesting day. This is going to be JTAG debug when we don't have a JTAG port. So this is probably going to be a fun, nasty debug session, but we're going to learn about JTAG and about the tap controller and about how do we debug this, which is never a very fun thing. Okay, so I went ahead and created the bit stream to do the JTAG, where we pass in the TDI and the TDO, we toggle the T clock, and we get and we save the TDO. I have two bit streams going different directions, and then the TDO is saved in the register, and the register goes out a wire. So hopefully this works correctly. Let's just do something real quick. So here we have our system, but I wanna do a quick update before we even get to this stage. Reprint out, and we can talk about what's happening here. So we're gonna print hex. I just want to prove that this is 0 and that I am not misinterpreting how this is supposed to work. So let's go ahead and get off my debug statements and just run this as is. So first off, let's show you a fun issue that you have with doing the internal JTAG. So if I do front panel and I program, this toggles the prog B, so it resets the FPGA. I now go here and I can see the FPGA, right? I see the FPGA. But as soon as I'm using the wrong one. So as soon as I program the JTAG bit, this is the magic of internal JTAG inside your FPGA. The FPGA straight up disappears. So I can't use JTAG to debug JTAG. Right? Yeah, it doesn't work that way. So we're gonna have fun looking at the tap controller today and other various things to try to get this to work properly. So this is going to, I gotta get rid of the front panel. So this is going to, okay, it is 0, and we get this consistent value. So let's talk about what's happening here. What is the value we should get? That's the important question, and I don't know the answer to that yet. So we gotta go figure out what value we should be getting. So the TMS starts off with lots of 1s. This gets into the reset state, and then it does a bunch of 0s, and then loops it back around to the reset state. I can show you this with the tap controller. So when we have, how many 1s they have in a row? They have wait a minute. There's the 5 is a 101. So they have 5 1s. So if we start off in the worst place possible, which is probably here, we go 1 1 1 1. So we're in test and logic, and we go 0 1 into the shift DR state. Is that the correct path, or should it be the three 1s? Or should it be a different path? 0 1 0 0, and we're shifting a DR. Okay, let's go. Let's figure out what JTAG. What does the reset do? What does test logic reset? So test logic reset does something. it sets the IR, right? So is this going to tell me what the test logic does? So we need to go look at this guy. So what happens in test logic reset? Test reset. There's a special operation when you reset the test logic reset. I wish I remembered what it was. Unless they're shifting bypass into everything, which is a bunch of ones. But it's a DR, not the IR. 0, 1, 0. That'd be 1, 1. Okay. Right, if we go to calculator, clear, we do a 0, 0, 5. Oh, no. 0, 0, 5, F. We're going to go 1, 1, 1, 1, 1, 0, 1, 0, which will get us in the capture DR state. Do we start with ID codes? Is everything, unless we're in a bypass mode and we're trying to figure out the devices. Yeah, reset puts everything into bypass. And then we figure out how many devices there are. And then we shift in all ones. The issue is, that my ID code is not working correctly. So if the TDI is set up like this, where it's giving 8 ones and trying to get something out of the system in the bypass mode, and bypass mode will give you one register and tell you how many devices are in the chain. Guess we could look at a legit JTAG target that I know works. Do we have anything like that? See, I don't really know. Easy way to debug the TMS and TDI messages. But if we go in here into the Python and we zero out the TDI and we rerun it, we get the exact same answer. Um, 3281 E4 184. That's 84. Is that consistent? There's a slight change there, so let's just see if that's consistent. Or we can make sure TMS and TDI are set up correctly in the VHDL. TMS, TDI, one is, okay, so yeah, have that set up correctly there. I mean, we could set up TMS to 0 as well, or what if we do TMS equals just straight up ones, right? What do we get out of this? We get ones. I want to make sure we got this in the correct order. So let's play around with what we got here. Okay, cool. We're shifting all zeros. Now we're going to do a single one. And why does it keep failing? Probably because I'm just screwing up the JTAG. Oh, we don't see anything until we start shifting data, right? Well, let's try to read the ID code. And we go to the UltraScale configuration guide. Let's go find the JTAG sequences. Hopefully they're still here. Right here. So here's a good setup. IR, the bypass register. This is when we do a IR shift. And we did what? 111 0 run test idle. Okay, all tests is stable in the controller, enabling the normal operation of the IC. The tap control statement is designed so that regardless of the initial state of the controller, can be entered. Only if certain instructions are present. For example, if an instruction activates itself, then it executes when the controller enters this state. 5 times. So that sounds right. Okay. So what we want to do is we want to be able to read the ID code. So we need to create our own sequence for reading the ID code. So let's do that. ID code is going to be that direction 5 to 0, this being the high bit and this being the low bit. So we'll want to shift in kind of the opposite. Oh, this will be fun. Let's try to shift in the ID code and shift out what we expect. Okay, let's do a raw JTAG sequence. So the way we're going to do that, we're going to copy this right here. We're going to do in this beautiful little section right here. And we're going to return after that. Okay, there is our print TDO comma hex this. Can we print this as a binary? I will do hex. Now we just need to set up the TDI up here. So we'll do length TMS equals, we may have multiple stages of these. Where's the 3 value? Yeah, we want that one as well. Okay. I mean, invalid syntax. The return statement. TDO. Okay, so we're gonna do length 20, and TMS we're going to set it to 1F, and then we're going to do and TDO was a bunch of high values, and we make this 0. Still a bunch of high values. It's doing zeros afterwards, so let's look at the tap controller. Oh, that's the bypass. We're doing the bypass. Do a second sequence of this. And yes. Okay, so what are we doing in this situation in the tap controller? So in the tap controller, we're doing 5 ones because that gets us into this state, and then if we do a bunch of zeros, we're just in the run test idle. Okay, now if we do a 1, we'll go into the DR state. So 1 0. Oh no, that's not how it works. It's a 5. So this is what we saw earlier. One E48132 000. Okay, what was the device? Okay, let's get the device name. So we're going to have to open up front panel real quick, program it with just a normal bit. My ID code. This is the value I want. So you'll put that under the return statement right here. ID code is, and what are we getting? We are getting, we have a 9. What if we just do those, what, 6 bits? Can we get this lined up correctly? Oh, front panel. The length not matter? Why is the length should matter in our TDO? Why does the length not matter? If I'm writing into the wrong port? Oh, that would be useful. Okay, let's do 6. That's weird that it went back. So if I do 20 on the first one, we get that value. What if we just insert an additional 1 here? What if we do FF7, right? Well, that won't change it. Okay. Let's pull out our calculator. So let's do the sequence 1 0 1 1 1 1 1. That's what we currently have, and we're going to do BF. Well, direction to do that in. And the value we want is a 4A. Let's type this out here. So we want a 4A 4A 64093 sequence like that. And let's get another calculator instance right here and look at what we have here. We have a what direction do we think it is? We gotta assume it's going to be highmost there, so let's go to a 1 clear x1 e 481329. Okay, now where does this line up? Does it line up at all? That really doesn't line up. 1 9 9 0 3. So I see the 9, the 3 right there. 2 101. Okay, I see the ID code. We're going the wrong direction. So let us do JTAG. Do the other direction. And let us go back to 5F, right? How close is this value? How are we printing it? Are we printing just the triggered out value? Okay. Okay, so what we got earlier was 1E. We're missing the first length. So we clear this guy. And what's the 4C? Four C 812780. Well, we're probably going the other direction. Oh. But the other one was a complete reversal. So I think what we want to go here is the 8 7 2 1 8 C4. No 3 1s in a row there. Where were the 3 1s in a row? Here. We ended with a 9. 9. Okay. Let's try this one again. So the 1E 4 8 1 3 2 2. There's the 9 right there, the 1, the 1 1, 0 0 1. It must have erased. So if this is true, we need bitwise, we need the other direction, which is what we did. Well, let's get another calculator. Is that 1E 1E48132? Yeah. So this is why I love decoding JTAG. It is bitwise manipulation that hurts my head, but it'd be really cool if it gets working. 4C81278. So okay, that's good there. There's the, so there is the 9 we see, which is right here. And so you're saying if we ship this one more, we would see a 9 there. Okay, so we'll try this pattern, but we're going to shift one more to the right. So let's do a 2 here and an F. Oh, look at that. So we have a A64093C. Ugh. We got it. So that's the ID code. We can read the ID code. So it's working like we think we expect it to. Now the trick is, how is the device expecting it to work? We may need to do some byte manipulation where we need to reorder the bytes, the nibbles. In this situation, how would we do that if it's the byte order? Now, that's the question, is what is the system expecting? What would the system expect in this situation? What happens if we do all Fs for the TDI? How does that change the answer? So it's somehow how the TDO is oriented. The byte orientedness. Maybe it's as simple as uncommenting this, which will do byte rotations. It's as simple as doing that. Hopefully. Or oh, why is that? Um, yeah, this is just swapping the. Wish I understood what that syntax did. So let's see what the tools thinks of this now. Too many devices. Okay, so we have to rethink how we want to return this value. Um, let's go ahead and set this for a 2F, so it matches kind of what we expect. Oh, we never fixed this, so let's do that where we have second TMS right here. Let's just you know, reset it for him. Okay, so four zero. So we have the A6, the 4-0, the 9-3, C7 in this situation. So how's this data going, right? Because this is 864093 C7. Where is the 4? What was the 4? Are we getting a bit off in this situation? The TDI shouldn't matter in this situation. I mean, like, if we shift in all zeros, or if we do zeros, we should get the same answer. Okay, so interesting, we get the 4 here, the 4 A6 64093 there, but in this situation, the second one, do we have what's up with the second one? We have bits left, TMS. Oh, okay, I know why. We're still screwing it up. There we go. Let's get it back into a steady reset position so we can figure this out. Reset. Why is this one coming out differently? Let's take this sequence that we do right here, and let's do it twice. So that's consistent there. Okay, let's try 11 on the oh, it's probably that last 0. What we want to do is shift that over. So the TMS, we want to make this so it's 300. We want to keep that 0 and just put a 7 there. Oh, an 8 there. There we go. There's some why getting off by 1? Weird. Well, let's try just printing the value there as well, because we may just be getting the correct value, but something along the way is screwing it up. Oh, it's not shifted all the way. Why wouldn't it be shifted all the way? Oh, because we would expect 12 bits in this situation. So let's go ahead and make it a 12. Do a 12 and then do 11 bits is so weird, right? Because that would be 8 plus 2 plus there's a 0 at the end. So we would make this a 7. Okay. What does this do? Our final answer. A64093. A46093 Okay, let's try the other direction. This may not end well. I'm curious to see what we get. So we didn't do, if we did the actual 11 for that. Sorry, this. So the 4 is getting cut off in that situation. How do I figure this out? Okay, that looks better. The data is actually getting loaded. But what if we need to just reorder the bits? How would we reorder the bits? That's just the bytes. So yeah, that's not going to help. That one is part of the ID code and that needs to be sent. So this isn't going to work. So what would be the correct? Well, let's do. All right, let's do the actual code that you want us to do. If this is true, then that is likely the 4 we want to see. So then what would be the issue? Could it simply be the Indianness? Because we're seeing it like, oh. But now let's change the Indianness. Go back to this mode. And what? We did this. This would put try that. Oh. I'm not sure what the other devices is, but we see it. Open target. If we unplug this guy, can we do, where are we? CDC slash, where's a good place? Why are we seeing too many devices? Can I get the temperature off this guy? Device. Help device. Device status. Targets. I really have the FBJF command. Well, let's see if we kill this. Disconnect. Close this. Targets, JTAG targets. Targets. Okay, so that one, it's not seeing anything correctly. Okay, I was hopeful for a second. So let's try. We try big. What does this give us? Really, it's just the same thing we had before. So this is a big to little Indian converter. So, the only thing I can think of is if we go to here and we create a new JTAG, and instead of doing, we do this, where we take a index to integer, and what is this going to be? So 0 would be the first bit. So we're gonna want what? 31 minus that. VHDL index array. Yeah. So we're going to want to do 2 integer. No matching subprogram was found. I don't know what you mean by that. I'm just indexing into you. Like if I put a 0 there. Unsigned value, what is it, bit count? Doesn't like that. Why doesn't it like that? Oh, this is still gonna have the same issue. So let's have it consistent. How are we gonna do that consistently? We want bit 0 to always go to the bit 0 spot. I mean, let's see if we can repair this in software real quick. So what you want to do is we just want to shift this value over by 31 minus oh. Take the bits left, and we want to shift this over by 31 minus bits left, and call that a day. And what does that do per se? Okay, let's do our fun little now let's return. That's good. Like how those values are coming out. What other way would you want it? Do you want the other direction of bytes? Oh, Python flip array. Okay, so reorder -1. Like, how else do you want the data given to you? Okay, so if we look at here, right, this would be the first byte. That would be the second byte. First byte, the second byte, the third byte, the fourth byte, fifth byte, and the sixth byte. But we did 11. How did that shift over so nicely? Yeah, that doesn't make sense. That shouldn't shift over nicely. shouldn't shift over nicely. 9.6. Okay. And if we go in and flaunt our dominance there, do a 2F, force a 2F in the first situation. 9340844. What is the ID code? The ID code is 4864093. Okay, I am going to take this as the final answer. Hopefully we get it working today, otherwise. Oh, that's good. That's good. That's good. That is good. Targets. Guys, it sees it. Open hardware manager. Open targets. Auto connect. Let me be able to read. Yes, we got it, guys. We'll prove it to you. Okay. Remove it. Still there. Do not program this. Do not program this. But let's open System Monitor. I am doing the Xilinx System Monitor through USB-C. We did it. We did it. Sorry it was painful. A lot of bit manipulation. Not really knowing what the code expects. Shall we? Do you know what happens if we try to program it from here? Do you know what happens? We can verify the device. That would be interesting. Let's verify the device. So we're running this JTAG, right? Let's verify the device. Please specify. I don't have a mask file. Do we have one in the build section? We're looking for an MSK file. MSK file. Wait, where did I build this? Yeah, I don't know how to do that. We can do a read back of the device. We can boot from configuration memory. We can program the keys. That'd be fun. We can do that. Okay. Perfect. So we just gotta clean up the hardware and maybe the software, but it's working. Let's add I don't know, VC init, VC BRAM, VC box. Okay. Okay, I'm just a little too excited. I got this working. Okay, we can remove that one so it looks cleaner. Do we let it fix in Python? Do we fix it in hardware? Well, eventually I want to do a much better version of this, which just shoves down the entire JTAG, entire thing. Okay, we'll call this V1. It functions. It works. We shouldn't be doing anything crazy with it, but it works. So tomorrow, we'll get it working with Microblaze and an ILA core, and potentially do the encryption as well. Woo! Okay. So maybe I can find a way to pipe this in. If we pipe it in, that would probably be the best option. Software-wise, it works for now. We'll figure it out later. Okay, well, thank you for joining us. I'm not sure who really cares, but we have JTAG through USB-C on the internal JTAG. We need to I need to find a way to make debugging a little bit more interesting. So basically the issue was, I'm basing this off of a core that Xilinx does, and they were expecting that my output, my shift register, to automatically shift everything to the bottom bit when it was done. So this what was the missing factor right here, shifting to the right. So I'm not sure if this is a good hardware solution or a good software solution. Hardware, it's like a shift register, and then we have to like bump it over to the end value when we're done recording. I mean, I kind of like doing it in software at the moment. I mean, software's already slow. We're already doing all this stuff right now, so I don't think it's a big issue. But let's go ahead and clean up all our print statements and rerun it to make sure that the print statements aren't doing anything magical, because they do sometimes. And let's go ahead and remove that. Okay. Okay, good. Let's stop with the large print statements all over the place. A little crazy. Go back here. We lost it, and now it's back. Woohoo! Do not program the device. Okay. I'm curious. Let's do something stupid. Who's with me? Let's do something stupid. Well, our JTAG crashed, right? It shut down. Okay, we can run this. We can run this again, and it will fix it. Did I break the JTAG? That'd be fun. Power cycle. Nothing like. Do not program the device through this JTAG interface. Okay, there you go. We have done it. Good night, everyone. Sleep well. I'm gonna let this run overnight, see if it does anything fun.